you have a question? Something? Any question? We'll continue on the lecture. Yes.
For the one the equation is just all the whole Lagrange formula plus the equation.
Yes. So the objective function plus lambda times the constraint. This is your Lagrange.
So you put the energy, the force,
Anything. Any question, please? So we'll continue. And I don't need to say that this is just a very new thing, right? Last time we just gave an introduction to optimization and calculus operations, and today we're going to really do optimization and calculus operations. So this is totally separated from the first half of the course, and you can start very, very fresh. Don't let things pass. And this is really the mathy part. It's very, very mathy part, and I warned you guys from the beginning, but you got so far now, and hopefully you're doing well. So it's very mathy. You have to start very simple in order to build up a very rigorous point, and you have to not let things pass, please. So I'll start by defining a function. What is a function? A function, F, is a map between two spaces, between two sets, between two groups, two entities. So it maps some set with some points x. This is a set x. It takes an element from the set x and gives you an element in the set y. This is a function, f. And if it's defined over the set x, it has to be defined over every single element. So it cannot reject any given point here. The function f, I give it an element in x, it has to accept it and give me something in y. Okay? Then we write it as follows. F colon, it takes values from x and give me values in y. We write it as this. F takes elements in x and give you elements in y. Okay? Like I said, if it's defined for all, if it's defined over x, it has to be defined over all elements in x. So everyone here has to be connected there. Okay? But not necessarily all the elements there will be connected, that's fine. But everyone here has to go somewhere, and maybe a couple can go to the same point, that's fine. Okay? And it can be that there are some elements there are left off, that's fine. So this is a function. Takes values from some set, gives you values in another set. And please, we have to think abstract. Don't confine yourself that a function, well, a function is something like x squared or x cubed at all. It's as abstract as this. It's as abstract as the following example. F is a map from days to fruits. Okay? We're not here in kindergarten, but it has to be as abstract as this. If you didn't take it seriously, you will mess up later. F takes Monday and gives you apple. Yeah, right? F takes Tuesday and gives you orange. It takes Wednesday, gives you grapes. F takes maybe Thursday and gives you apple again. Is this a function? Yes, it is. As long as it is well defined, meaning Thursday I'll get apple and every Monday I'll get apple again, that's fine. But I cannot come in the next Monday and get something different than apple. Then this is not a well-defined function. If you like to know it in terms of your functions, usual functions, then this is a function, x squared, f of x equal x squared, is a function. When you give it Monday, -1, gives you 1. When you give it another day, right, it gives you the same value. So that's fine. This is a function. It can take 2 x's from here and give you the same value for 2 x's. That's fine. But it cannot be the other way around, such that it takes 1 x and there are 2 possibilities for x. This is not a well-defined function there. So if I do it the other way around, x and f, something like here, this particular x has 2 possibilities. This is not a well-defined function. Okay? Any question about that? Any question? I'm saying we will go very, very rigorous in math. We will be very mathy. If you don't understand these simple concepts, I guarantee you that you will screw up. Okay, we'll talk about differential geometry, which is a nightmare for mathematicians themselves. So, yeah, you can just go and Google it. So we have to be very simple from the beginning. Any question about these things? Okay, so let's have some examples that we know. Maybe f from real line to real line. What do you mean here? How to interpret this? F takes a real value and gives you a real value, right? Something like f of x is x cubed. This is a function, right? Maybe f from R3 to R. So what's this? F takes
3 values.
3 values, 3 real values, and gives you a number. Some example, f of x, y, and z is x squared plus yz, right? Takes you 3 values, real values, and gives you a number. Okay? F is a map between, we said it's as abstract as anything you can ever think, right? First, what is that? What is CAB? CAB here is the space of continuous functions. So f takes an element from that space, i.e. f takes a continuous function. Its input is not a number, it's not 3 numbers, its input is a function. And gives you what?
A number.
A number. Like, give me an example. Here it is. F is the integral from 0 or from a to b x of t squared dt. F of x. Okay? Here was f of x, here is f of x, y, and z. Here is f of x of t, right? It's a function of a function, right? A function of a function. Give me a function, I give you a real number. Before we used to this. We used to give me a number, give you a real number, give me 3 numbers, I give you 1 number, 2 numbers, whatever. But here this is a little bit new. Give me a function, I give you a number. Because if you give me your sine, I'll put it sine squared integrated between limits and I'll get a number. Give me cosine for every input, right? For every function, I'll give you a number, a real number, okay? A function of a function, we have a name for that, we call it functional. When it's a function of a function. When the input to your map is a function, it's not a number, we call it a functional, okay? And the output is a real number. Any questions so far? Yes, please.
On the last example you told, can there be a form of function without any integral? Because how else will you...
Yeah, I give you another thing. What about this? Very simple. F of x of t is dx by dt at some point. Right? Differentiate the function, substitute by number, whatever it takes, whatever form it takes. At the end of the day, I understand this as give me a function, I'll return you a number. Okay? Any question? Okay. Then we can now distinguish between finite dimensional optimization and calculus operation very easily. This is the finite dimensional optimization that we use too. This is 2.6, which is a very important course to any engineer. I highly encourage anyone who didn't take 2.6 to take it. It's an indispensable course to an engineer. Optimization is very essential. At any rate, what's the given for an optimization problem? What is required? Typically given some function, I'm going to call it J, that maps Rn, right? You have n design variables, n unknowns, x, y, z, or x1 up to xn, and I have a function of these x's that takes all these x's and return what? Real number, right? Usually we have a function of several variables, and I want these variables to minimize that function, right? So I'm given this, and what is required is find x star, the optimum, which lives in Rn, right? It's x1 up to xn, such that j of x star is less than j of x, right? For all x. Maybe in Rn or maybe in the neighborhood, depending on what it's a local or global minimum, right? Anybody has a problem that this is the definition? This is the mathematical definition of any finite dimensional optimization problem. Any question about that in our language, which is actually the standard language? Any question? So I'm given a function, and I want to minimize it. I want the minimizer. Okay? So calculus of variations, on the other hand, what we're given? We're given a bunch of things, actually, not just a single function. First, I'm given f, some f, that's function of three variables. First is something in this interval between t0 and t1. Takes three variables. I could write R3, but I will write it like this. Okay? And gives you a real number. So it's a function of three variables, just like we used to. Function of three variables. Takes three variables, give me some real number. Okay? What else we given? We given J that takes an element. You remember C, AB over there? What was C, AB? Was the space of continuous functions. We put 1, then this is differentiable. Put 2, and this is twice differentiable, and so on and so on. So C1, this is the space of differentiable functions over this interval. So J takes a function as an input and returns you a real number. So J is called what?
Function.
Functional. Okay? J is defined as the integral between t0 and t1 of this guy. F of t, x of t, x dot of t. dt. So we're given all this. We're given the function, and we're given the functional. Okay? We're also given 2 points, t naught, x naught. I'll give you some time to write, but you have to bear with me for a minute. T1, x1. Okay? So what is the description of the problem? I'm given all this, and it's exactly the same. Find x star of t. It's a function that lives in the C1. I need a differentiable function. Find x star of t such that j of x star less than j of x for all x in the neighborhood or in the C1. Okay? Yeah, if you came a bit late, probably this is now mystery. So let's see the description. What's the description? I mean, what is the interpretation of this thing? This is t, maybe time, this is x. And we are given 2 points in the xt domain. 2 points. T naught, x naught, and t1, x1. Okay? Find x star t that is differentiable such that it's minimum and it satisfies the endpoints. X star of t naught is x naught, and x star of t1 is x1. So I'm given 2 points in the xt domain, and I'm looking for a function, x star of t, that connects these 2 points. Maybe something like this, like that, right? Any function that connects these 2 points and minimizes this j. We agreed from the beginning, in this definition, that j takes a function and gives you a number. So for every shape, j will take your shape and give you a number. And I'm looking for the shape that results in the minimum number for j. Okay? This is the problem statement. We didn't learn how to solve it yet. Like here, this is the problem statement of 2a6. Any question about this? We're going to know how to solve it today, but first of all, we have to understand the problem statement. Any question? Like I said, this is pretty new, right? And I guarantee you that it's never been taught in any undergraduate course almost in the entire planet, so it's not expected that you guys know. That's perfectly fine if you ask questions, okay? If you have any question, don't let it pass. Yes, you.
Can you explain the C1? Why did you name the C1?